Good morning, everyone. My name is Hyun Park, and today I'm presenting on Introduction to Splines, focusing on regression and smoothing splines as covered in Chapter 7 for Problem Set 7. Here's our agenda for today. First, we'll quickly recap what we've learned so far and motivate why we need techniques like splines. Then I'll explain the core concepts behind regression and smoothing splines. After that, we'll walk through a set 7 problem to solidify understanding. Finally, we'll look up at real-world application of these methods in finance. Let's begin. So, what we've learned and why should we learn this? So far in chapter 3 and 4, we focused on linear models like linear regression and logistic regression. These models are great. They are simple, fast to compute, and highly interpretable. However, their main limitation is that the strict linearity assumption. If the true relationship between predictors and the response isn't linear, these models can suffer from high bias. In chapter 6, we looked at refinement like Rich and Lasso. This helped by reducing model complexity and variance, often improving the prediction accuracy, but they are still fundamentally linear and can't capture truly nonlinear patterns. So, why do we need to move beyond linearity? Look at this example, and simple line misses the curve in the data. Our goal is to create models that are flexible enough to capture nonlinear patterns accurately without becoming overly complex and overfitting the model. Chapter 7 introduces several ways to achieve this, including polynomial regression, step functions, and the main focus of today, splines. So this is our problem set 7. It asks us to sketch the curve head of G that smoothly fits a set of points based on minimizing a combination of residual sum of squares and a penalty term involving the mth derivative of G. The key parameters here are lambda, controlling the penalty strength, and m, controlling the type of smoothness. So before to solve this, we should study splines, smoothing splines, and the key lambda, m and m. So let's get started to the concept explanation. Many nonlinear models, including splines, can be understood through the basis function approach. Instead of fitting y directly to x, on x, we fit y on basis functions denoted b1x through bkx. The model still looks like a linear model, but now it's linear in the transformed variables. This allows us to model nonlinear relationships using the familiar framework of linear regression. Polynomial regression and piecewise constant functions, also known as step functions, are specific examples of this approach. We add terms like x squared, cube of x, and so on as parameters. This allows for curves, low bias model. However, high degree polynomials can become overly flexible, leading to high variance and strange shapes, especially near to the data boundaries. Step functions divide the range of x into bins and fit a constant value in each bin. This is simple, but creates discontinuities, jump, and can miss the underlying trend within the bins. So regression splines offer a better alternative. They combine piecewise and polynomials. The idea is to divide the range of x into segments using points called nodes. Additionally, we put constraints on a model for smoothness. As the figure shows, a simple piecewise cubic fit is discontinuous. Forcing continuity makes it connect, but the join isn't smooth. A linear spline is simpler, requiring only continuity. A cubic spline enforces continuity of the function and the smooth curve at a node. We lose some flexibility with each constraint, but gain smoothness. Then, how do we represent this mathematically? We can use a special set of basis functions. For a cubic spline with k nodes, we typically need k plus 4 basis functions. A common choice is the truncated power basis shown here. The function h, x, and c basically activates a cubic term only if the x is bigger or same with cushy. Isn't it same with the ReLU function? Then why we use this truncated power basis? This slide shows mathematically why the truncated power basis works. The smoothness means the first and the second derivative to be continuous. When you take the first and second derivatives, the terms involving cube of x minus c becomes 0 when x approaches to the node c from the left. It shows 0 in the left-hand limit. Then on the right-hand limit, you can see that uh, they also approach 0 as x approaches to the right side. This ensures the derivatives match up at the node, creating a smooth transition. A practical problem with regression splines is choosing the number and location of the nodes. Too few nodes lead to high bias, meaning underfitting, while too many nodes lead to high variance, meaning overfitting. Smoothing splines offer a solution with it. Instead of selecting nodes, we place nodes at every unique data point, creating a very flexible basis. Then we control the flexibility using a penalty term. We minimize a combination of the user RSS to fit the data well, and a penalty for roughness of the function g. In the formula, there are two key players in the penalty. One key tuning parameter is lambda. It controls the trade-off between fitting the data, minimizing RSS, and the smoothness penalty. If lambda equal to 0, there's no penalty, and the spline will interpolate the data to minimize RSS. It will become 0. If lambda approaches infinity, the penalty dominates everything, forcing the function g to be as smooth as possible, which might lead to underfitting. We typically choose proper lambda using cross-validation. The other key player is m, the order of the derivative in the penalty term. It determines what kind of smoothness we're penalizing. If m equal to 0, we penalize the first derivative g prime. If lambda exists, the integral of g prime of x squared will be smaller, forcing gx to be smaller to a constant function. If m equal to 2, the most common choice for cubic smoothing splines, we penalize the second derivative double prime of g, meaning double prime of g to be smaller, so gx will become similar to a linear function. If m equal to 3, we penalize the third derivative g triple prime if we think about extreme case like lambda equal to infinity. The integral of g triple prime of x squared will be smaller, meaning g triple prime x equal to 0. So gx will become a quadratic function. It's like an extreme case. So to think about is if lambda equal to infinity, then it happened. But if lambda is just a proper number, then gx is gonna be near to linear function, near to quadratic function. Problem solution. Okay, now let's apply these concepts to solve the problem introduced earlier. We need to sketch the resulting curve ahead of g for different scenarios of lambda and m. Please say lambda goes to infinity and m equal to 0. The infinity lambda means the penalty term must be 0. The penalty is the integral of g of x squared. For this integral of a squared function to be 0, the function itself must be 0 everywhere. So ahead of gx equal to 0, the sketch is just a horizontal line at y equal to 0 regardless of the data points. Case B, lambda equal to infinity and m equal to 1. Now the penalty is the integral of g prime of x squared. This forces the first derivative g prime x to be 0, meaning gx must be a constant. Which constant? The one that minimizes the RSS term. That's simply the mean of the observed value y values, y bar. So the sketch is a horizontal line at the average y value. If lambda equal to infinity and m equal to 2, the penalty, the integral of g double prime of x squared forces the second derivative double prime of g of x to be 0. This means gx must be a linear function, gx equal to beta 0 plus beta 1x. To minimize the RSS, the line will be the standard least squares regression line. If lambda equal to infinity and m equal to 3, the penalty, the integral of g triple prime of x squared, forces the third derivative g triple prime x to be 0. This means gx must be a quadratic function. Gx beta 0 plus beta 1x plus beta 2x squared. To minimize RSS, this will be the least squares quadratic fit, which is typically a parabola. This is a different case. Lambda equal to 0 and m equal to 3. Now lambda is 0, so the penalty term completely disappear. We are only minimizing the RSS. With no smoothness constraint, the function g can become arbitrarily complex to fit the data perfectly. So the solution will be an interpolation function that passes exactly through every data point xi, yi, making the RSS exactly 0. As the sketch shows, this function is extremely wiggly and represents severe overfitting. It has captured the noise, not just the signal. This corresponds to a model with very high variance. Let's explore about the degree of freedom, complexity. For a cubic spline using the truncated power basis, the degree of freedom are 4 plus k. For the base cubic polynomial intercept x squared, x cubed plus the number of nodes, so k plus 4 degree of freedom in total. A potential issue with regular splines is high variance near the very boundaries of the data. Natural splines address this by adding extra constraints. They require the function to be linear beyond the boundary nodes. This reduces variance at the edges, giving more stable extrapolations, as seen by the narrow confidence bands for the red curve. Now, mathematically, as we solve that case C to make linearity constraint, we can force the second derivative double prime of x to be 0 at the boundary nodes. This leads to constraints on the spline coefficients. So the first boundary to be linear constraints 2, beta 2 and beta 3 equal to 0, and the second boundary to be linear. There are two constraints. Some of the beta k plus 3 become 0, and some of the beta k plus 3 multiplied by c, k becomes to 0. It is because of derivative, and we can calculate it by a little bit of uh, algebra. Uh, in the case of cubic splines, for the boundary, constraints has two constraints for each of the binaries, 80 to 4, and ordinary splines, cubic splines have k plus 4 nodes, and we minus 4 from them, so the degree of freedom of natural splines become k degrees. Now let's get to real-world application. I chose the estimating yield curves with splines, which is a little bit old thesis research paper, but it is really important to calculate the real-world uh, estimating for the statistically in the uh, money count. The yield curve shows the relationship between a bond's time to maturity and its yield. It's crucial for understanding market expectations. The challenge is that we only observe yields for specific maturities. We need to estimate a smooth curve for all maturities. Simple model methods often produce unrealistic noise or jagged curves. The paper from 2004 uses penalized splines, which is a type of smoothing spline for this. This figure shows their key idea, smoothing simultaneously over both calendar time t and time to maturity m, resulting in this smooth 3D surface representing the entire term structure evolution. By taking slices of that 3D surface at specific points in calendar time, we get the estimated yield curve for that day, as shown in these plots. Notice how smooth the curves are. This is thanks to the spline's ability to balance, fitting the observed data points with the smoothness constraint imposed by the penalty. This allows for accurate interpolation of yields at unobserved maturities. Now, this is the end of the video. Then thank you for your listening. Then I cited Introduction to Statistical Learning textbook and IRCLP labs and my own MLD and Notion page and the research paper estimating the term structure of interest rates using penalized splines. Thank you for listening.